In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium.
A whole skit on me.
All right, hello and welcome everyone to Celestial Theodolite update number 24. Today we're going to be going back to the basics and kind of give a top-down overview and walkthrough of the process, the mechanics of how it works, and the basic fundamentals of it, so that it can be understood. So that before we get to talking about the data and the measurements, etc., we actually have an understanding of what's being put forward in the first place, and how we are using the Celestial Theodolite to externally test an internally consistent model. So I think tonight we're going to be joined by Coco and one other, if we can get a Flat Earth lad to join as well. So we can do, we're going to play a game of Do You Agree? And we're just going to kind of go through units of measurement, how the sky is divided up, how fast it moves, etc., and just kind of set the baseline for what we're working with, so that we can understand, what the data, what the end product of that was. So if we have any Flat Earth lads that want to play, Do You Agree? Volunteer now. Was that Hasbro PSYOP? I saw your mic go off. Did you say something?
That was me.
You in? You in it to win it, my dude?
I'm in it to win it, bro. I got free time for the next couple hours. Let's get it.
My freaking guy.
Presentations, by the way, bro. Thank you.
TY. All right, Coco, are you there, lass?
I am here.
Fantastic. Okay, we'll go ahead and start the game in a minute. But before, I have a quick announcement to make. There has been a lack of celestial theodolite measurements as of late. The weather, the people have been busy, etc., etc. So we put together a little slush fund from the Ether Cause lads. And what we're going to be doing is, if you live in the southern hemisphere, you can do some celestial theodolite measurements and submit them. You will be paid $50 per mountain peak that you record. Now, you don't get paid per star or whatever. You can use the same peak at different distances if you want, multiple payments or whatever. But yeah, that's what we're putting out, a bounty for celestial theodolite measurements. So a quick recap of what you need to do to participate. All you need to do is go to wherever the location is you're going to be shooting from. If you can get a daytime picture of the location, that would be awesome. So we can, in case we need to do comparisons and tracking down the stars and whatnot. But the most important thing you need to do is write down your latitude and longitude of where you're recording from, and then identify the peak that you're shooting. So you can use an app like Peak Finder. It has a large database in it of all the peaks around the world. And when you overlay it and look through your phone, it'll tell you what peak you're looking at. So just give us that peak name and give us your lat long that you started the recording from. And then on top of that, but there's one final hurdle to overcome. We need the exact timestamp of when you started the video, and we need your frame rate. And if you can sync your recording time to GPS time, that would be fantastic. That would make it super easy. So that's all we need is your lat long, the mountain that you're shooting, the name of it will suffice. We can do everything else on the back end, and then just give us your recording information. So if it's, I think we can probably figure out the frames per second too if we had to. So really, we just need the time synchronized to GPS time. So if you have timestamps that you can put in the recording, or if the file name that's created when you start the video or whatever puts the epoch of when you started it, that's all you need to do. And you can collect your $50. So how to collect the $50?
Yo,
yes.
Alan, you wouldn't happen to have that Bluetooth thing still on, would you? Because you got some weird interference coming on a little bit. Maybe it's just me.
Did anyone else hear anything?
I didn't hear anything.
I heard
Nothing
a beep.
that
I heard it. I know what
I
you're talking about.
noticed.
I heard what you're talking about.
Okay.
I definitely heard something. It sounded like someone was like on a seesaw in the background or something.
Yeah, it was like a high-pitched whistle or whatever. I felt like if you're using your Bluetooth thing before that was super annoying, that might still be connected. That's what I was hoping it was.
From death metal in my ears.
All right.
Can't
All right. Enchiladas. Inshallah, it's off. But
There you go.
all right, yeah, thank you. I didn't realize I was on. Okay, so how to collect the money? My email address is AlanSpaceAudits@gmail.com. That's ALAN space audits, all one word, no underscores or anything, at gmail.com. Just send me an email of where I can download the files and whatnot in your PayPal or your Cash App, and we will send you the $50. So that goes for Southern Hemi lads. And then also, if you live in the Northern Hemisphere, if you live at sea level or 200 meters above sea level, you're also eligible. So we need some sea level measurements, and different angles and stuff would be nice. So whatever you can come up with, if you live in the Northern Hemi, if you want to record some stars, get $50. You get $50 per peak. So that's the offer on the table that will add to the data set. And then I'll make a more formal written out thing here in a bit, and you guys can reference that or whatever. But yeah, we are looking for people to participate in the measurements. Okay, so now that that's out of the way, I think we're ready to begin on the celestial theodolite. So Coco and Hasbarap, what's your name?
That's Noah.
Noah. Okay, I thought so. Noah. Okay, Coco and Noah. Okay, so this is a game of do you agree? This is how the sky has been divided up into 360 degrees, and you can also reference your appendages to get some rough angle measurements. So if you were to hold your finger up to the sky, the width that your finger takes up would be 1 degree. If you hold up 3 fingers, it's 5 degrees. A closed fist makes 10 degrees. Index and pinky out make 15. Index and thumb, I'm sorry, yeah, what is it? Pinky and thumb come out to be 25 degrees. Does everything make sense so far?
Yes.
Yeah, that's pretty cool. I did not know that.
Yeah, that's pretty awesome. And then another way to conceptualize this is they actually take smaller measurements that are called arc seconds and arc minutes. So you can actually take this 1 degree here. So if you take your thumb and hold it up to the sky and imagine that you have 60 sheets of construction paper, and you could arrange them such that they're not touching, but they're just equally dividing up your finger, you can divide that 1 degree up into 60 minutes. 60 minutes equals 1 degree. Now that's a thick piece of construction paper to make the arc minutes, but you can also break a minute down into 60 seconds because there's 60 seconds in a minute. So imagine you had even thinner sheets of paper, just like regular plain paper, and you could divide those up in between the ones that you did for the minute, and then then in between those you'll have 60 sections for 60 seconds to equal a minute. Does that make sense?
Yeah.
Yes, it does.
Awesome. Okay, cool. So if we hold our fingers out, index to pinky, we can make a nice 15 degrees, right? So if you hold it up at the sky and you imagine a star at your index finger, 1 hour later, it'll be at your pinky finger. If you were to hold your hand up for an hour in that same spot. Make sense?
That's pretty cool. Yeah, it does.
Awesome.
Yep.
Okay, so we already went over the breaking down of the minutes and seconds using the paper analogy, but here's what it looks like in math form. So 1 degree is equal to 60 minutes. 1 degree is 60 minutes, and then you could break 60 minutes into another 60 seconds. So you can break 360 degrees into 3,600th of a second. And it's just basically, if you'll notice here, that's just an extra 0 on a 360. So it's just kind of, that's the interval of how it extends. And then when you get into, we're not going to get into it here, but they have micro arcs and milli arcs, I think, which just extend that out. So they get down to 3,600,000th of a degree and then 3,600,000,000th of a degree. But for the stuff that we're going to be talking about here, it'll just be down in the arc minutes mostly. And we might round up some arc seconds if it comes close to an arc minute. Okay. So because we know that this will return back in 15 degrees per hour makes 360, we know how fast it can go. So we can do the linear velocity equation and determine exactly how fast the positions of the stars are moving over the Earth. Now, whether or not the Earth is a globe or flat or stationary or what have you, like a geocentric view, either way you slice it, the ground positions of these stars to complete that 360 at 15 degrees per hour can be made into a linear velocity. So if you have the circumference of Earth and that 24-hour period in seconds, you can do velocity equals circumference divided by time. So that's just distance over time. And that will give you 486 meters per second. So that's how fast the stars are moving over top of us at the equator, I believe. I think I have that added on the spreadsheet. So does that make sense so far? Like the rate of movement is proportional to these angles over time?
Makes
sorry,
sense to me.
I'm sorry, 464 meters. I might have said that backwards there.
Can you just re-say that real quick for me?
Yeah. So we started with angles and time, but because we have the circumference of Earth, so we have like a distance for them to travel that 360 to complete it, we could take the full completion of that circle, which is the circumference. So we could take 40,075 kilometers and do over 800 or 86,400 seconds. That's how many seconds are in 24 hours. So we could just take how long it would take.
I,
Sorry, go ahead.
I have a question.
Yep.
As per the circumference or whatever, wouldn't a glober just claim the circumference is different? Like the equator is the maximum circumference, and then as you go north or south, you get smaller and smaller circles.
Yes, absolutely. You can actually do the cosine of wherever the latitude is, and that'll give you the linear velocity at that location. So actually on the
Okay,
spreadsheet here, we have we'll start with, I'll just show you real quick. At Pikes Peak, Colorado, I think the latitude was like 38 here. So if we look at the equator reference in imperial units, we have the distance at the equator is 1,038 miles an hour, or 1,522 feet per second. And then if you go to if you do the cosine of the latitude, you'll get 1,185 feet per second. So that'll be the rate of change for that. But yeah, it all equals out to what it would be based off of the circumference at the equator either way. Because it's still completing the same circuit. Yep. All right, Coco, are you good on the distance over time conversion to get how fast the stars move over the ground in terms of if you were to get your speedometer out and clock them?
Oh, so you had almost gotten to that part when Noah asked his question.
No worries. Okay. So distance over time, we have the circumference of Earth. That's how, like, if you were to hold your finger up and that star was directly above you, like just looking straight up 90 degrees, it will take, it's going to traverse 40,075 kilometers, and that's going to take 80,000 or 86,400 seconds. So we could just do circumference divided by time, and we can get how, like, that linear speed per second.
Right. So I'm going to give you that's how you get that. I'm going to tell you ahead of time, though, that I'm not really going to remember that calculation.
Oh, that's perfectly fine. It's basically
Okay.
like if you're familiar with, like, they say, the Earth rotates at 1,000 miles per hour at the equator or whatever it is roughly. This is how they determine that. Basically, it's just like, long story short, this
Okay.
is how they came up with that.
We're trying to get to the conclusion that the angle determines time. So we're going to
Yes.
establish each
Yeah.
independently and then put them together.
Yes, because the globe model, celestial navigation, etc., as done with the celestial sphere model, is predicated on angles equaling time and vice versa. So if you know what time it is, you know the angle to the star. If you know where that star is at, based on its angle, you know what time it is.
But doesn't the objects move at a different angular speed depending on what, like how far off the ground, how far from the horizon they are? Like, don't they move slower at the center of the sky versus faster at the equator or something? At the horizon, something like that.
No, that's a really good point. So going from your zenith to about 20 degrees, or probably 10 degrees, they travel at 15 degrees per hour, and then as it gets at those lower angles, there's a lingering or looming effect. Now, this could either be due to optical circumstances of our nonlinear vision, or it could be in a combination of refraction, or it could be solely due to refraction, as the globe mainstream asserts with astronomical refraction. But yeah, when it gets lower in the horizon, it doesn't follow that 15 degree per hour relationship anymore. But to keep and to explain why they're still visible at those locations and not following that 15 degrees per hour, they just invoke whatever astronomical refraction would be required to keep the star at that angle so that it maintains usefulness for its ground position.
I almost feel like that's somehow fallacious for the globe to kind of like
So
they're asserting like, go ahead.
yeah, no, I kind of felt the same way, but kind of think about it like this. The only thing that actually follows the 15 degrees per hour is called the true position of the star, which is this. Just if you were to view a star transiting over your head at 90 degrees and you were to take a snapshot of like the time that it was there, it would come back exactly at 15 degrees per hour, but only in that band of being directly above you. And what they do is they project out that true position. So like they take that snapshot from that original zenith measurement, and then they just go, okay, that's moving at 15 degrees per hour. But then they separate that position, that calculated math source position, from the apparent position. So as you get to different angles, they're like, oh, it's actually refracted up. So you're no longer seeing that almost 1-to-1 position of the star from when it was at your zenith. You're seeing an apparent image of it. And then as it gets lower, they're like, oh, the apparent image is separated from the true. But the light source true position does follow the 15 degrees per hour, but the apparent position does not.
I understand.
Awesome. All right, Coco, making sense so far? Still good on that?
So far, I think I'm following it. Thank you.
Awesome. And then just real quick to reiterate on the true positions and stuff, right? It starts off as just, hey, I'm looking up 90 degrees above me and there's a star. And then how long does it take to come back? And it came out to be 15 degrees per hour. But if you apply that same 15 degrees per hour to the optical star that that same star that you're seeing as it gets lower, it doesn't follow that rate. So to come up with the difference between the two, they just say it's refracted a bunch. Okay, and then we're going to get
Yeah,
into...
I understand what they're saying. I don't know if I agree with it, but I do conceptually understand it. So I'm just going to go with yes.
Yeah, awesome. Yeah, the conceptual understanding part is super important because we're actually going to use the principles of the light source is movement versus the apparent motion that we see from what we see in the sky as part of the occlusion process. And then as it's going to turn out, the true positions when they intersect with physical objects, we're no longer able to see the star, which gives some indication to the way that I kind of conceptualize it is that there's a true source star somewhere. We don't know where it's at, but what we see is always the apparent thing. We never see like the actual source of it. And like if you were underwater looking up at the sun, and you know how it's like displaced in the water, like that's kind of what we're looking at. We never see the true thing, but we can reference it. You know what I mean? Like mathematically.
See, I would agree with you. And I believe like that description you gave earlier of the non like truth, like that's also the glober. I think even the globers agree, dude. We all agree we're looking at an apparent position. Well, the honest globers all agree.
Yes. Yeah. Even in their model, it's apparent in both the sun, the moon, all celestial bodies are apparent. Sorry, was there a question? I thought I heard someone.
Yeah, Alan, it's Shalom. But just letting you know that your audio for you is great on YouTube, but the participating audience on Discord is super low. I don't know if you could do anything about that.
So I also have a question when you get a second.
Yeah, go ahead. You're good. I think I fixed the audio. Should be good.
Okay, so I don't really know anything about astronomy or anything else, so I always just thought when I was looking up at the sky, I was looking at the light coming from that actual star or planet and stuff. But you're saying that's not what we're seeing?
Yeah, you're seeing like the after image of it essentially. Like in the mainstream model, they say that, the distances are so far away that the light coming to you takes time to travel. So what you're seeing is actually like where it was, a couple of minutes ago, depending on its distance and whatnot. So you're kind of seeing the after image.
So you're assuming that the star or planet behind the light is moving.
That is the implication, yes.
Okay.
Yeah.
So you're using. All right, I'm going to say this really badly because it's mixed up in my head. So you're just going with where the star was at the time we can see the light for it.
Sure.
Kind of. So when we get to the occlusions and like the self-theo process, we're going to reference where the true position was, because the occlusion and an emergence is a physical process, which we'll get to here in a second. So we do end up referencing where the true position was. If you were to like conceptualize that as like this is the source of the light rather than the after image that we see, we do reference that, like that's the primary separation from what we do versus how the mainstream globe would like us to conceptualize the positions.
Okay. I think I'm following what you're saying. Thank you.
Yeah, awesome. So like just real quick, if you think about, instead of a star being hella far away and whatnot, just think of like a flashlight overhead that's moving really fast and it's super far away. It's like, there's going to be like a little separation between the actual position of the light that you're seeing from the source versus where the source is at, if that kind of helps conceptualize it a little better.
Yeah. Yeah, I do think I'm following that now. Thank you.
Awesome. Okay, and then next up we have units of measurement. Now this is a really important concept because we often get told that units of measurement are mutually exclusive to a globe, all distances are globe distances, et cetera, et cetera. But what a unit of measurement is in terms of meters, I like meters. All the imperial units can be converted back to meters through multiplying it by like 3.993 or something, whatever it is. So they're all a ratio of the meter. So we're just going to stick with the history of the meter because everything has to be backwards compatible with that. But what they started with was using the terrestrial meridian for the length of a meter. And the terrestrial meridian is defined as the distance from the North Pole to the equator. So like a line of longitude going from the North Pole to the equator. And if you were to break that line down to 1/10,000,000th of a segment, that 1/10,000,000,000th would be what a meter is. That would be the distance of a meter.
So that means it's 1,000,000 kilometers from the equator to the North Pole.
Nope. 1/10,000,000,000th is a really small number. The equator to the North Pole multiplied out in nautical miles or meters comes out to 6210 or 6218, depending on what you do. So if you take that 6218 number for kilometer, like that's what it would be in kilometers. If you break that down into meters, it would be like 6 million something, 6 million, 6218. It would be six.
So it's not a 1-to-1. The meter's not like a 1-to-1 with the equator. I'm confused at what you.
It's
10 million meters if you do it in meters. It's like 10 miles. So like, you're getting all units mixed up, I think.
Oh yeah, sorry. No, it is 1-to-1.
10 million or 10 billion? I'm confused.
Oh, 10 million?
No, I said it wrong. It's 10 million. I was thinking of angstroms because what they ended up doing is redefining, well, by combining wavelengths of light. There's a unit of wavelengths called an angstrom. That's 1/10,000,000th of the same thing. But so I got that confused. But yeah,
So
he's right.
60
It's 1/10. It's
6210s.
1/10,000,000th.
6210 statute miles, 10,000 kilometers, or 10 million meters. So it's all equivalent in this ratio system, right?
Ooh, thank you, sir.
That's what I got. What Shane said, that's what I got from it. So I guess I'm correct in my understanding. So yes, I understand.
Awesome. Correct. Or awesome. And then Coco. So I know I kind of fumbled that a little bit, but if you think of like a string going from the North Pole to the equator, and then if we just cut off like a little bit of that string, that would be and then we use all units of measurement as a ratio of that little segment that we cut off, but it's tied to the bigger segment. You know what I mean? So it's all a ratio of the same thing. Does that kind of make sense?
Yes.
Awesome. And then that actual length is defined by positions of the stars where they're at and how we see them. So multiplying out a unit of measurement derived from the system itself is always going to be internally consistent. So what do I mean by that? Well, if you take 2 points of longitude, you can do the cosine between them, and you can get a distance. It'll calculate. They'll call it an arc circle, or what is it? The arc length. All of that is derived can be derived from doing the cosines of the latitudes. So so it'll produce a number in meters that you can traverse in meters, and it's going to be internally consistent. So in other words, you're not going to find a contradiction in pulling up like Google Maps and going like, okay, I live here. I'm 15 miles from the library. And then you get in your car and you go 15 miles and you're like, oh, like, it's not going to give a different number. Does that make sense? It's going to be internally consistent because that's how the whole system works.
Okay.
Awesome. And then I just had some more history on the meter and stuff here, but it's basically everything I just said. And then just the history of it. So if anyone wants to check out those, there's links provided there. And then here's the coefficients that link, or how you can multiply an inch back to the speed of light, because they got together in, I believe, the 80s and redefined it from a terrestrial meridian to the speed of light that it travels in 1 second in a vacuum. But you could link that to 239.37 inches, which comes out to be consistent with the meter anyway. So it's always, while it appears to be like a new separate unit of measurement, it's actually still just ratioed against the original terrestrial meridian for internal consistencies. Because if it actually came out to be like a different thing, they would have to like redefine distances and stuff. And we've never heard them do that, right? But sometime in the 80s, they changed the the definition to the speed of light, and none of our distances changed. Well, the only way that would be possible is if it's part of the same ratio. And then what you can do further is you can actually break light into a spectrum and measure the physical wavelengths specifically and the distance between them. And so that's what they do now to define a meter, because it's super accurate. No worries, Coco. Yeah, the way they used to do it before was they had like a little, what was it, iridium bar or whatever, and then they would measure it at 0 Celsius or something. So it's like the wavelength of light thing is way easier to do. All right, so that was distances, and then distance calculus.
Is that
Go ahead.
match the meridian? Like it's matching the meridian, but they just standardized it as like this wavelength of light, kind of like the atomic clock is supposed to match the
Yes.
solar
Yes, that's exactly.
year. But okay.
Yep.
Well, they took the same length and they were like, "Ooh, this is no longer 1/10 millionth of a terrestrial meridian. It's actually 1/299,763 over the speed of light." And you're like, "Oh, ooh, neat." But both of them still equal 39.37 English inches. So the unit hasn't changed. What they did was historically recontextualize what they ratioed it against, but it still remains 1/10 millionth of the terrestrial meridian.
Oh yeah, okay, understood. Got it.
Well said. Well said. All right, then we got distance calculation, which I didn't put a thing here for, but we're all familiar with the Haversine, the elusive Haversine. It's supposed to be mutually exclusive to a globe, because it requires the radius value to calculate with. Well, if we're dealing with a spherical coordinate system, which is latitude and longitude, and you're computing distances between it using central angle theorem and the cosine of that, well, you're going to need a radius for it to be, to use that. So that's all. Like our position is that it's just math to calculate the positions between the stars. The curvature is in the sky, not the ground. But that's how we're not going to not use the Haversine. There's also a couple other ways we can do it, but none of the ways to derive distances is mutually exclusive to a globe, although it is framed that way through the coordinate system being spherical. A lot of people say that the coordinate system represents the ground, etc. But this is going to be a test of that. But in terms of deriving distances, no matter where the curve is at, sky or the ground, this coordinates using sign formula with the latitude and longitude and all that will yield the correct result because it is internally consistent. It's gonna output a unit of measurement that's a ratio of the original terrestrial meridian and or speed of light, which is just the same thing that Shane just went over.
Keep in mind, you can't have a terrestrial meridian outside of a latitude-longitude grid system because you can't get 62 statute miles unless you can do 90 degrees of separation. You get 90 degrees of latitude. You can do 69 miles per degree to get 90 degrees of latitude to get 6210. Only within that coordinate system is those calculations even possible. So then the unit becomes a metric of the coordinate system itself, which is what we mean when we say internally consistent.
Yes, sir. Well said. All right, now we're gonna. Oh, cool, dude. Canva's hilarious. It's gonna play both videos at the same time. 1 second. Gotta fix that.
Ooh, maybe you didn't pay them enough.
Okay, we're gonna watch a couple of videos real quick, and then we'll go over them. All right, a quick lesson on the principles of the cell Theo. So what we're looking at here is you can see the pattern of that light is distinctly different from the lights that are in this hallway here that are being reflected out into the mirrors or windows there. But what you'll notice here is that the reflected beams, so like this right here, gets reflected out into the images, and as we move over, we can see that when we intersect the reflected image, it doesn't block the light. The direct light source is right there, doesn't get affected when we move into the reflected images, right? The only thing that actually blocks that light is the physical object, and we must overcome that to see the light again. Okay, so what we're looking at here as we move, you see now it's in the reflected image, no occlusion. Same concept as the cell Theo.
That's a cool video.
Thank you. Yeah, so basically, if we consider that street light the source of the star, and then, us moving back and forth to create the relative motion of what would be an occlusion of an apparent object, we see that the true source is unaffected by the apparent object. So it requires the intersection of the source and a physical object in order to cause an occlusion, and then also to see the emergence, we had to move past it to be able to see it again. And then we could take another look at that from a video from Taylor, where she used a laser pointer and a knife and a glass of water to kind of show the same exact thing. So we'll watch that now. No. Hi, this is me, Taylor. I have a laser and I'm shooting it into a glass of water. As you can see here, when it intersects with the physical object, the light gets occluded. When it's next to the apparent object, the refracted light doesn't get occluded, and you can see it sticking out through the refracted image. Thanks, Tay-Tay.
You could have asked her. She could have just done a live rendition.
Did you not just hear her? All right, so next up we have Goose, who made a little jig here to kind of show the same thing with the intersection point of the true object versus the apparent, and how it requires a physical intersection before it gets occluded. So here we have the jig with no refractive obstacles in between the light source and the object here. And we have this black one here. This is going to be our observer. So what we're going to look at is a camera on the ground here looking at this black object, and when it's lined up with this object in the middle here, we're going to see how much further this light source that's on the end of this has to be behind this before it gets occluded for the observer on this side of it. So to kind of show what that looks like, if you were to take a stick and line up these two, you would see that the observer and the object are directly in line with one another. And when you when there's no refractive medium between them, now obviously there's refraction in air and all that, but the distance is real short, so we're just truncating it to a nice clean zero here. But as you can see here, the angle of separation that's created to actually occlude the light source from the observer over here when these are directly lined up is just, it's a really tiny angle here. You almost can't tell the difference here, but let me see if I can zoom in. See this little line here? There's definitely an angle there somewhere. So we can see that's a really tiny angle. But then when you put a refractive medium in between there, it's going to take that light source and bend it around it a little further. So it has to move further away to actually be intersected with the physical object in here and not the refracted image of what's in here that the observer is seeing over here. So when you do that and you put the stick back, you'll notice that the angle is definitely bigger here, way bigger. So that's the significance of the occlusion being a physical process versus an apparent process. Now, a lot of what we started with when we were going through this self-theo and the process and everything, a lot of the globe lads wanted to add terrestrial and celestial refraction together as if a refracted mountain could occlude a star, and that's not the case at all. It would like set into the mountain and then it would get occluded in the mountain. It would vanish while it's like inside of the mountain, if that were the case. So, let's see. I think we could play.
Hey, Alan, could you explain that just a tiny bit more? I'm just a little lost on that. Just a little bit.
Yeah, let me. I got some.
Thinking,
go ahead.
I was thinking to maybe not bring up the mountain part when you were dealing with that, because I was trying to catch on, and then you started talking about mountains.
Okay, no worries.
And I got lost.
No worries. Let's say that this knife here represents the mountain. It's just a mountain, right? Like the physical mountain, as if there's no refraction. And then when you put this knife in this medium, we see that there's an extended version of the knife that comes out here. This is the refracted part of the knife, right? Does that make sense?
Yeah.
Okay. So if there's going to be an occlusion, the light source that Taylor's holding here has to be blocked by the physical light source. It can't be blocked by the apparent refracted, lifted up, reflected image. See how it's like sticking? See how the light source is like, it appears as if it's shining through the knife?
You should play it. Yeah, nice.
So it doesn't actually get blocked until it's physically blocked by the actual knife.
Yes,
That's
sir.
the significance. Exactly.
Yes, sir. Exactly. So if the stars, if it worked the way that the globe lads were saying or whatever, we would see the stars going into the mountain before they would disappear in the mountain rather than being, occluded right up towards the tippy top of it. So that is the significance there. The occlusions are a physical process. It can't be a refracted light versus a refracted image. They'll never occlude one another. So that's the significance of that. And then I'll play out Goose's jig video here. We can watch that. So this is from that perspective of being next, on the ground at that black peg, and then it's lined up directly with the object that's going to do the occluding, the yellow peg here. We got the lights, light source on the right, and it's going to move to the left, and we're going to see the occlusion differences based off of when there's no medium versus a medium. Same situation with the knife.
Wait, what's this part where we're seeing the peg separate?
This is when he's added a refracted medium in it, and we're looking at like a refracted image of it.
Is there supposed to be sound?
No, there's no sound.
Okay.
Yeah, he put that cup over it, this right here that has the water in it. So now we're looking so now we're looking at
And he was just lining it up, right?
Yeah.
It's super refracted though.
Yes. But yeah, that's what we're looking at as he gets that lined up. We see it's finally occluded there, and then he'll get the stick out and put it back, and we'll see that there's a change in the angle there. That's lame. At the end, we didn't see the end result, but that's what produced the larger angle there in that screenshot from the video. Sorry about that.
Yeah, I was gonna say that video maybe should have some kind of narration to
Well, I did
explain
That's
what's
fair.
going on.
that is fair. I did all the narrating before we watched it, but yeah, you're absolutely right.
Yeah, and I'm just saying that then when I went and watched it, I guess I was paying so much attention to it, trying to understand it, that I did not match up what you said with what was going on.
No worries, no worries. We can do a
Because-
quick recap just off of the screenshots if that's easier.
Well, I mean, I don't want to make you go back and do all that, but there was that. I guess there was just really two parts that it really started losing me, and the one had to do with when you said the new angle.
Ah, okay.
And
so let me.
I didn't see the new angle.
Yes, I got
Yeah,
you.
don't show this. Don't show this. I do photography, so I know what's going on here. So this part confused me with what was trying to be said with the other part.
Okay, so
But the actual where you went and showed the angles with the pegs again, and right as you put he puts the refractive material back on it.
So basically, all he was doing here is just showing how much further the light source had to move so that it was still in alignment with the actual object.
And yeah, this part I got.
Okay, that's all. That's all.
It was where.
Just another example showing it has to be physically in front of it. It can't be it can't be obstructed by a refraction.
Yeah,
although
so
I do like the knife one better.
Yeah, so it's like if you were to take the knife example,
Yeah, it passes through.
Yeah, if you were to say like how much further did Taylor have to move this laser behind this object if the glass was empty versus filled with water is all this was. That's all this was. Just showing how much further it had to be moved. All right. So if the occlusion process is clear enough, we can move on to stars in the ground.
So it's just that the image of a knife can't actually physically block light from passing through the medium is the whole point. Am I correct?
Yeah, only the actual physical knife part could block it.
I mean, that makes sense to me. Yeah.
It's pretty straightforward. Sometimes we tend to overthink it because it's like, oh, like what are you saying again? But yeah, it's pretty much all it is.
So would you say that's why sometimes you could see like stars through the moon per se? Is it being refracted into a position to where you can see through it?
That would be a possibility, but I have never seen any stars going like I've never seen that. But I mean that would be the implication.
Interesting.
Yeah. All right. So we got stars. So we covered how the object in the sky move at a certain rate. That we could turn that into we could turn that rate of degrees into minutes and seconds of an angle, and we can also turn that into real seconds and minutes of time. So if we were to take the example of just watching a star and then we no longer see it anymore, did it get occluded by the ground or is it just out of our vision? Like this is something that's been, long contested on in the globe Earth versus flat Earth paradigm here. But so far we've agreed to, the motion and the treatment of how occlusions work, being a physical process and whatnot. So when we no longer see the star, we have two possibilities: that it was occluded by the ground because of Earth curvature, and it's now being physically obstructed by that, or it's out of our limit of vision. Now, like Noah pointed out earlier, when the stars are following the 15 degree per hour, when they get down to about right here, that's where they start to linger. And we can see what that looks like on a graph here in a second from our good buddy Brian. Let me see if I can pull it up real quick to show that lingering copy. Now, let's see, copy link. There we go. Copy link. All right. So if you were to plot that out, the stars, would ideally be following the celestial sphere, so they should be right on this dotted line. But as they get further into the horizon, you see they kind of deviate from that 15 degree per hour that's created by the celestial sphere, following that ideal radius. But that's all we're looking at there. And someone's microphone is a little hot while they're typing.
Got it.
All right, cool. So now we need a way to test what's causing the occlusion. Is it the ground or is it some optical phenomenon? Well, Mike ingeniously came up with the idea that we could use known elevations of mountains, because that creates a new variable that's not just observation of a thing disappearing at the horizon. That can't tell us anything unique about the situation. We could argue our positions until we're blue in the face, but until we introduce another variable for this analysis, we can't come to any meaningful conclusion. But now we have a mountain peak. I'll start with the globe first, since it's most familiar to everyone on here. Now we can test now when this star should be occluded by the mountain peak, because we know how fast it's moving, we know the rate, we know how fast it's going to traverse the ground distance between us and the mountain peak, and we know when it's going. We can use astronomers' tools to look up references for where the true position of the light source is going to be versus the apparent and all that stuff. So now what we can do is we can, instead of using the horizon, we can now use the elevated horizon which is created by this peak here. So if we know the mountain peak, we just do some plain trig to get the elevation, and then we also get what the globe would predict for the elevation being lower. So on a flat Earth, the mountain is never going to be lower physically due to curvature. It's going to be the actual height. So we can compare the angles of the actual height versus the angle if there was curvature, just by subtracting out what the drop over distance would be from the elevation of the peak on the angle. Because the thing with trig is, once you have two of the variables, you can derive the other one, and from that ratio. Go ahead.
Does everyone agree though that would be different for globe than it is flat? The time at which that star goes in front of that mountain due to the geometric difference and drop over distance between the two would occur at a different time. Do both people agree with that?
I don't know enough to agree or disagree with that.
No worries. Let's
Logically,
yeah. Instead of thinking of the mountain, just think of the knife. You know, on the globe, the knife is going to be lower. On a flat Earth, it doesn't matter how low the knife looks; it's always going to be the same height. So two different angles are produced by the math to make the prediction. Because on a globe, it would be physically lower, right?
yeah.
All right, and then
Did you get
that
that, Coco? Right, there's 2
No,
different
I
predictions.
didn't get that at all. I have no idea
Okay.
why a mountain would be lower on globe Earth
globe?
than flat Earth.
It's tilting away from you. Think about it, right? You got a flat Earth, right? Same elevation,
Oh,
pretty much.
so this is a mountain.
So the mountain would be physically lower if it's tilting away from you, if you think about it, right?
Okay, so we are assuming that this is a mountain that's somewhat over the curvature.
Yep.
Or
Yeah.
essentially, yeah. Where
Okay, so we're starting out with it lower just based on the fact of how far away we are from the mountain.
you got
Yeah,
it.
the key
Yep.
fact is we're observing it from a certain distance away. Right.
Got it. Oh, thank goodness, because I
So-
really had no clue what was going on there.
You're good. There's
And-
basically 2 different predictions and then 1 observation to decide which one's it's closer to. But go ahead.
So yeah, if you go back to that other slide, Alan, now we can look at when we were comparing the two. Yeah, like so now we understand why those two would be different. So we both agree that that star would go behind that mountain at a different time for a globe as it would for a flat Earth, right?
Yeah,
The-
that makes sense. If you're a distance off from the mountain, on a flat Earth, the mountain would be whatever X height away. But
Yeah,
on a globe, it would be whatever height X away, subtract from the curve, like how much it's curved down, and then also subtract a little bit off the top of the mountain for the angle that it's tilting away. So yeah, it would be. I have to agree that the globe Earth would predict it's shorter, right? Unless there's some sort of, unless we account for refraction, which I'm sure that's what they say.
Hence the point of the knife and everything else.
This is my favorite illustration though, because Ruhif put it out. Right, the glober that all the globers look up to, and our good buddy Ruhif put this out. So it's not really a misrepresentation of what the globe argues, and it quite explicitly shows the difference between the two. You don't really have to know about the angles and the distance. You just have to know that one of those mountains is higher than the other, right? It keeps switching from one to the other, and the bottom would be the lower for the globe. The globe has to be a little bit lower than flat Earth based on how far away you are when you're looking at it, as we all just agreed.
Well said. And yeah, Noah, real quick, what you said earlier, you can actually convert the drop over distance to an angle by just doing the inverse trig function for it, and then you subtract that from the angle from the flat Earth angle, and that becomes the globe angle. That's all this is doing right here, essentially.
I'm looking at it. It's nice. So that minus 202 is.
So that's the difference between flat and globe over 50,700 kilometers. It's 202 meters. Any formula you want to use, engineering, 8 inches per mile, will come out to 202 meters. So the difference between those two angles when we're doing basic trig is that drop in distance. Is that drop over distance, 202 meters. That's why the top one, the only difference is that is subtracted from it. That makes the angle resulting lower. And right, so it's a smaller triangle. It's a lower height.
Wouldn't it be even lower though? Because the mountain would be tilting away from you slightly on a globe.
It would be exactly the drop over distance converted to an angle and then subtracted out. So instead of being 231, it's 217. Because like what we found out is that how they're always like, oh, that's just an approximation. That's just an approximation. Well, there's this thing called central angle theory, and what we what we found is that the drop over distance is always proportional to it's always half of gamma. Half of gamma is, I'm pulling it up now so you can see it. All right. Okay. So this gamma here is the central angle. This angle, this is derived from having 2 points
Oh, nice.
that subtend
Nice
a
right there.
sphere. So what you're doing, when you would trick out the distance for this to get the drop over
You use
distance,
this?
it's always half of it. Yes, we use central angle theorem for it.
Oh, nice. Okay, yeah.
Yeah. So when they say like it's just an approximation, could be more, it could be less, it actually can't. It's always half of gamma. So and then the full amount, it gives you the celestial drop, which is we're kind of getting into some deeper concepts here, but it's not just an approximation, it's actually what it mandatory has to be to follow this trigonometry here.
I just want to say, Coco, don't feel bad for like not knowing anything. This has been a really awesome presentation so far. So with the back and forth and stuff.
Yeah, I wanted to say, Coco, you're doing great. Don't feel bad. You're crushing it. Clarifying the things that we overlook are great.
Yeah. Interrupt whenever you don't
I
understand
know.
or you think we screwed up or whatever, or nothing's clear. Yeah, whatever.
I know what I know, and I know what I don't know. So, and
Nice.
yes, this is actually helping me a lot
Awesome.
more than those other presentations. I'm sorry.
Yeah, no, well, a lot of them, we've been through some of the stuff and we're so familiar with it, we often overlook, stuff or like we'll make a giant leap and people are like, how do you get there?
Yes, and you're not the only one. I know that this happens because of my father. He was like way above everybody, so he often spoke way above people, and I had a feeling that's what was going on.
Nice. Yeah, well, the purpose here is to always make it as accessible as possible. So like Shane was saying, if you need any clarification, feel free to just say, hold on 1 second, need help. Okay, so that concludes, I think we got the basic principles covered. We got angles, time, distances, physical processes, and the differences between flattened globe for physical occlusions producing different angles. Absolutely crushing. So now we can get into what I like to call the spreading of the sheets, which just means we're going to open up Google Sheets. Pause for laughter.
If you want to go through like the flagship example of Pikes Peak, so that we know like what we're talking, and then we can, because I think we need that. If we need to go through all the from beginning to end, I think distance, drop over distance, we have all the components, right? So we can work it out and why the two angles would be different, maybe.
Got it right here.
Because the rest of it is just going to be a bunch more data based on this. So this is like the template, the rubric for how you do it one time.
Yep. Okay, so let's see. Let me see if I can pull up the video real quick. Download Celsius stuff. Yes. Documents. Unlucky. I didn't download the Celthea videos. 1 second. I was gonna show Mike's video real quick before we get into the data. Yeah, do you have it real quick?
I think that's converted and downscaled. Let's see, which one is that? That's 4 minutes, so I don't know which one's 39 Aquaria in this video though.
I don't even think that's Pikes Peak, big dog.
I labeled it Pikes Peak.
I'm gonna go ahead and say you mislabeled it.
39 Aquaria. Okay, how about this one?
Hang on 1 second. We're gonna do we're gonna do Pikes Peak, but we're gonna do not the 39 Aquarii. We're gonna do the one with the moon in it because it's cool as hell. So give me 1 second. Okay.
That is actually 39 Aquarii just below the moon.
Oh, nice, dude. Even better. Thank you, Mike. Okay.
I forgot you were here to help us out. That would have so much easier.
Okay. So Coco, you know how I had that picture in Canva of like the globe and the flat earth with the mountain and the star?
Yes.
Okay, so now what we're looking at is Mike with his video recorder, and he's facing a mountain, and we're going to look at a star as it hits the mountain. So this is when we talk about, occlusions and doing the celestial theodolite, etc. This is what is happening here. So that star is following its, 15 degree or so-called 15 degree per hour. It's actually at a lower angle, so it's not going to be at the exact 15 degree, but it's following that relationship there that we talked about earlier for that linear velocity. And boom, see it hit once it goes behind the mountain, it's no longer visible. So at this point of the agree or disagree, I think we can conclude that the star is no longer refracted for us as we can no longer see it.
Okay. And refraction is because we are seeing the light from the star and not from where the star actually was at the time.
Well, refraction happens. No, hang on one second. You kind of. So
okay, I messed that up. Okay, forget it then. Forget it.
No, you're good. We can make sense of it. So what we're looking at here is the refracted, apparent position of the star, right?
Yes.
And then as it gets down here, it's occluded. So what we're saying is that the true position, that laser light source that Taylor was holding, we can think of that as the star, that is now physically lower than the mountain. Or, not physically, it's a bad way to word it, but it's now lower than the mountain. And what we can determine from that is that because of the source being lower than the mountain, the apparent light that we see can no longer overcome the mountain.
I had a question.
So prior it was, sorry.
Oh, this is the part that loses me a little bit. So when the refracted light gets blocked, that doesn't really speak for the source of the light, does it?
Yes, completely. Yes, because only when the light source is actually blocked is when we'll stop seeing the apparent position. Because when we go back to this.
So you're saying it was being refracted or up above the mountain previously until.
Yeah, everything we see is refracted. Yes.
Right, but what I'm saying is the refracted light reaching your eye is what's being blocked, not necessarily the point source of the light.
No, that's specifically what's being blocked, the actual point source. That would be the implication. Because what we're going to turn around and do is reference where the true position of that star was, that light source was at the time of occlusion. And if it's at the same angle as the peak on a globe or on a flat Earth, that's going to determine the physical elevation of the mountain that did the occluding. Because if it was just an apparent object always, then it would never get occluded, right?
Right. What I'm saying though is if the light is bending, that light being bent, the target source, the target of the light is what's not reaching your eye anymore. That doesn't necessarily speak to where the point source is coming from. Right? You can block the light. If the light is bending, you can block the light.
No.
Without being able to determine that the point source is directly behind that.
No, only when the light source is blocked.
If we had to apply like a coefficient for the amount of refraction, when you no longer see the star, what would you apply? What would you apply it to? It'd be 0. Right? So you can't apply to nothing. If you don't see it anymore, you can't have an amount of refraction that you're arguing for.
Yeah, I get what you guys are saying. I think I need to think about how I'm wording what I'm trying to say.
Yeah, no worries.
I'll get back to you.
No worries. We can do a quick recap of.
I'm still trying to wrap my head around the implications of this. Oh shoot, sorry. I didn't realize I have a hot.
No, you're good, man. I mean, anything we can do to help. That's why we do this every week, man. But let me see. I should be done lagging now. Testing 1 2. Testing 1 2.
That's so good.
Can you go back? Can you go back to the video where you were showing with the
So only when we get a physical object do we stop, are we unable to see the reflected light source.
Right. So I understand that the mountain or the physical object is what's needed to block the light. It can't be a refracted object. I understand that part. What I'm saying is if you were to technically leave that same light source in the same spot and add more curve or take away curve, you would get a different point at which that object would block that light. Right? The
Yes.
point source stays at the same point,
Sure.
but the bending is affecting where it's going to get blocked.
Yes. That's exactly what Goose's thing was showing, with how the angle increases because the physical intersection angle had to change.
So that's where I get a little lost of, okay, we understand the bending is what affects where it's going to get blocked, not the actual location of the source of the light.
Nope, it's the location of the source that light, when it finally intersects with that they can no longer bend. That is what determines the occlusion.
So in this circumstance, the light source is the moving object, correct?
Correct.
Okay.
You lose me there, but I don't want to hold you up. It's okay.
No, you're good, man. I'll try and think of some more ways to break it down. But yeah, basically what we do is when the star is no longer visible for us. So in that video that we watched earlier, right, when that's no longer visible for us, what we do is we hop into Stellarium, we enter the coordinates of this peak, and we look at where the true position of that star was at the time, because we're considering that the light source, the source of when it was once measured, taken from a zenith measurement, and then adding 15 degrees per hour for that, we're considering that to be where the physical source would be located. And then that's what we're referencing. So if that angle happens to match the angle for the observer there, then that means that the star is parallel to the ground. And what you could actually do is draw another triangle from the peak to the star, and then have a flat baseline from the peak, going parallel to the ground. And this angle would be the same as the original angle, which implies that there's no drop over distance.
That clarifies it very well. That's perfect.
So the time is the determining factor, right? Whatever the time that the star went
Yeah.
directly behind the mountain, we convert that to say, all right, does that equate to 231 or 217? 2 degrees 31
Yeah.
minutes, 2 degrees 17 seconds. And we go to Stellarium and we look at the time, because we know divided by 360, as we started with, we can reference an epoch, which is just a starting position or a point of zero. We add the correct time to that, and we get the so-called true position of that star. We're using that position and its correlation to time to determine a model, because that time becomes our mutually exclusive piece of evidence. And so that's where we had to agree on that time, and then we could see whose model predicted closest to that time. In so doing, we're accommodating the difference between flat and Earth with the stellar occlusion.
Well said. And yeah, so here's what it looks like to hop into Stellarium. We enter the coordinates. Here's observer chords, and then we should have mountain chords somewhere. One of these two. But anyway, that's what we do to determine, what the cause of the occlusion was, because just doing it from the observer location doesn't actually tell us the cause of the occlusion, right? Because as we just learned, or went over, man, that's so annoying. I'm sorry. I apologize, guys. My internet's not cooperating. Okay, it seems to be back. Okay. Let's see here. Holy sheet. Can post that sheet again. Absolutely. You want some sheet? One sheet. All right. Where were we at? Converting angles into time. So we're verifying what angle that star was at that time at the peak. And if that angle is closer to 230 than it is 216, or 217, actually, it's a rounding thing right here. This should be 217. But depending on which one that is closer, that determines what the cause of the physical occlusion was. And if the Earth is a globe, then we should be measuring an angle here when we go to confirm. It should be closer to what the globe predicts right here for Pikes Peak for the drop over distance, and it doesn't. Or it ended up being occluded at 233, so it was slightly higher than what we predicted.
Now, would the Globers just argue that that was just due to refraction and that's why? Or is that.
Oh, they argue something entirely separate. They argue that going to the mountain peak is not allowed, can't do that, doesn't work, this method's stupid, doesn't mean anything, non-physical, they actually completely reject that analysis on the face of it. They have never once accepted that as a valid analysis. They confine it to looking at it from the observer location and only the apparent position.
For obvious reasons, right?
Implications, man.
The implications, exactly. You can sense them coming and you don't like it, so you get off the road. Sorry, Coco, what?
So to be very stupid, where is this 230 and this 216 coming from?
Oh, no, that's a perfectly valid question. So, like I talked about earlier, there's two different predictions that could be made for globe and flat Earth. And all you do is just do rise over run for the peak. So we know the distance and we know the elevation of the peak because we can look up what the elevation is, and we know how far away from it we are because we can, enter our coordinates and then use a distance calculator to the latitude, longitude of the peak and get the distance. So that gives us our rise over run. When you divide those together, you get a degree in radians, and we can convert that into degrees, and that's all this is. So it's just dividing the elevation of the peak over the distance to the peak, and that gives us an angle.
Of where the peak is supposed to be or where the star is supposed to be.
Where the peak was at the time it occluded the star, right? That's what we're shooting for.
Yes, great question. But it is the peak, and there should be no physical relation to the occlusion and the peak at that elevation if the Earth is a globe. Because if they both match, then that means we can make a congruent triangle, meaning we could just say that this angle for flat Earth is the same as the angle from the peak to the star, because that's what it would imply geometrically. I think we have some images of that, what that looks like. Here we go. So ignore all the math on here for now. Just look at the triangle. We have a distance of 50 kilometers, and we have an elevation of the peak of 429 or 4,299 meters. We can divide those into each other and get an angle that's 231 for the peak, as if there's no drop over distance. And then when we take when we record the occlusion and the time, and we go to the peak in our favorite astronomer software, and we look at where that star was at that time at the peak for its true position. If it's also 231 or thereabouts, well, now what we can do is, you see how this white arrow turns into a blue arrow that just keeps going, and then we have another white arrow that goes off the side here. That's making a congruent angle off of the first one, and that would only be possible if the Earth were flat. Otherwise, the angle that it would produce would be congruent with the globe angle here, which would be 217, but it was congruent with 231.
Again, the difference between those two is just 202 meters. That's what the difference between 231 and 217 for an observer who's 50.7 kilometers away, and perspective on a flat Earth or a globe Earth. It's only different 202 meters. So the mountain would be 202 meters lower for a globe, which is why you get 217.
Nice.
Do globers claim refraction from the star to the mountain?
Yeah, they do, and also they also claim the refraction, like terrestrial refraction. So they also they don't want to agree to the 217 angle. They want to add two arc minutes of terrestrial refraction to make it 219 because that's what a terrestrial theodolite would measure. But we're not interested in the optical for number one, and number two, the refraction wouldn't, as we just went over, the refracted mountain would contribute nothing to occluding the star physically. So that's not even a tenable position.
And then number three, when you add it, it doesn't even make it closer. We still are much closer. So it fails 3 times.
And on top of that, I was looking through the differences between astronomical refraction and terrestrial, and I found some great resources from Andrew Young, who's like one of the most prominent and cited globe lads that covers refraction. He actually goes over the history of how they tried to merge terrestrial and celestial refraction back in the day for geodetic surveying and whatnot, and it leads to a ton of problems. They can't do it, and mechanistically, terrestrial.
I think you're back.